Welcome to a special Halloween bonus lecture. I'm going to show you in this one how to use matrix decompositions that I went through on Monday's lecture in Python. This will give you a reference implementation that you can compare your own to. So I've got a Python notebook here, a Jupyter notebook. The first cell, I'm going to import two libraries. One is a big scientific Python library called SciPy, and I'm only going to import a submodule called linalg for linear algebra. We'll probably use more of this library later. The other one I'm going to use is NumPy, which I always use. That gives us essentially our matrices and vector. I'm going to do this in Python, but I'll do another one with C++. So I've loaded those libraries in. And the next, I'm going to create random 5x5 matrix. I'm going to call it A to be consistent with what we've got elsewhere. It uses this NumPy library, and the dot means I'm going to use routine from that library, and then random, so the random library, sub-library in NumPy, and then the random routine, and in it I pass in a sequence of two numbers. In this case it makes it two-dimensional and 5x5. So these are random numbers, they're between 0 and 1. There we go. Now if I use linalg.lu, I'll put a question mark, it'll tell me about it. It does. A matrix decomposition, it breaks A up into three matrices. On Monday I talked about two of them, the L and the U. But there's another one, P. It's a permutation matrix, and this is used for numerical reasons. Whenever we do an LU, we do the Gaussian elimination, get the LU decomposition, we divide by the ratio of the element on the diagonal to these different elements. If this element at the top is small, we end up dividing by a small number and we can get numerical problems. What can be done is to reorder matrices into a different order. They're just simultaneous equations. So in this case I could take the larger value, this 0.9, and shift it up to be the first equation, so I'll be dividing by that. I think that's what we'll see in a second. So now let's call that. What it returns is 3, P, L and U. I'm going to call P, L, U equals np linalg, and I'm going to pass it my matrix. Now I can print them off. I get L. As you can see, this is a lower triangular matrix. It's got ones on the diagonal, just a convention that we're using. And then we've got these other elements here. We've got U, it's the upper diagonal, upper triangular matrix. And if I do np dot, so this takes the dot product, or for a matrix that's defined as matrix multiplication, L and U. Let's compare that to my original. So what I should see is I've got the same matrix, but the rows have been reordered. And the reordering is controlled by this permutation matrix here. Essentially I've swapped the first and fourth rows. I compare these two, see the first and fourth have swapped, and you get the idea. You can work through the permutation, see how it's switched the rows around. So if I do np dot p, and then that's dotting np dot L and U. So this is P times the product of L and U. I should get back my original matrix. Okay, now let's actually use this to solve the problem. Let's make our right hand side matrix. This time I'm only giving it a single number in there. I'll cover it in. Print off. 5 is the source term, the right hand side. Now if I want to actually use this in our matrix, I do the factorization and then I solve using it. So I get LU and PIV, which contains the same thing as the permutation matrix. Funny. So it's going to be lin al dot fact. Okay. LU. Now if we get LU, see we've got more or less one of our matrices from before, with a list of how we've reordered things. This pivot matrix is going to tell us which rows we've swapped when. So it contains the same information as the permutation matrix, but it's just written in a slightly more convenient form for the computer. We don't actually look at those. We can now do x, our solution vector, equals lin alg dot lu solve, and we pass it lu pivot and our right hand side matrix, print off x, and there we've got our solution. So if we do np dot a x, could get b. There you go. That's how to use the LU functions inside SciPy library. Started off, we just used the call. We got the individual elements. We could look at them and compare them. Then we do it in 2 steps. The reason for doing it in 2 steps is, as I said, you want to create the decomposition and then you can use it all the time. I've only got to call the factorization once, and then I could solve multiple times the different right hand sides. And the factorization scales cubically with the size of the matrix, but the solution scales quadratically, square. Much faster if you've done it. You can use this, I put it in the lecture notes, to solve for the inverse of a matrix. You can use these methods to find the determinant of a matrix. Have a look in it. Thank you.